Copper is everywhere. Inside power cables, electric motors, smartphones, computers, solar panels, electric cars, charging stations, and entire power grids. Without copper, modern civilization as we know it would simply not work. But almost nobody thinks about where copper actually comes from. You don't dig copper wires out of the ground. You don't find shiny copper bars hidden in rocks. Copper starts its life as ordinary stone. Deep underground, copper exists mixed with other minerals, sulfur, oxygen, and massive amounts of useless material. This mixture is called copper ore, and in most cases only a very small percentage of it is actually copper. That means producing copper is not about melting a metal. It is about separating a tiny amount of valuable material from enormous quantities of rock. The entire process begins in mines. Some copper mines are deep underground, with long tunnels stretching for kilometers. Others are gigantic open-pit mines, enormous scars in the landscape, visible even from space. Every day, these mines remove thousands or even millions of tons of rock. The ore is blasted or mechanically cut, loaded onto massive trucks and transported for processing. At this stage, the material looks completely unimpressive, just broken stone. But this stone contains something incredibly important. The first step is crushing and grinding. The rock is broken into smaller pieces and then ground into a fine powder. This is crucial because copper minerals must be physically separated from waste material, and that only works when the particles are small enough. Even after all this effort, the powder may contain only a few percent of copper. Everything else is unwanted material that must be removed. And this is where chemistry, physics, and industrial engineering truly take over. In the next part, we'll see how this fine powder is transformed into a copper concentrate using a process called flotation, the step that makes large-scale copper production possible. Once the copper ore has been crushed and ground into a fine powder, the real separation begins. At this point, the material is a gray, muddy mixture that contains copper minerals and a huge amount of useless rock. Visually, nothing about it suggests metal or value, yet this step determines whether copper can be produced efficiently at all. The powdered ore is mixed with water to create a thick slurry, and special chemical reagents are added. These chemicals are carefully chosen so that they attach themselves only to copper-bearing particles. The waste material remains unaffected. When air is blown through the mixture, something remarkable happens. Tiny air bubbles form, and the copper particles stick to them. These bubbles rise to the surface, creating a foam layer, while most of the unwanted rock sinks to the bottom. This process is called flotation, and it is one of the most important technologies in modern mining. Without it, separating copper from rock on an industrial scale would be nearly impossible. The foam containing copper minerals is skimmed off, thickened, and dried. The result is called copper concentrate. Even now, this is not pure copper. Typically, it contains only about 1/5 to 1/3 copper. The rest consists of sulfur, iron, and other elements. Still, this is already a huge improvement compared to the original rock. Now the material is ready for the next major transformation, turning mineral concentrate into metal. The copper concentrate is transported to smelters, where it is heated to extremely high temperatures. During smelting, chemical reactions occur that separate the metal from sulfur and other impurities. What emerges is a molten material known as copper matte, a rough intermediate product that contains much more copper than before, but still not enough for real-world use. This molten material is further processed through controlled oxidation. Sulfur is removed, impurities are reduced, and the copper content increases again. Each step brings the material closer to usable metal, but the copper is still not clean enough for electrical applications, where even tiny impurities can dramatically reduce performance. At this stage, copper looks like copper. It is solid, metallic, heavy, and unmistakable. Yet from a technical perspective, it is still unfinished. To reach the level of purity required for power grids, electronics, and high-performance motors, copper must go through one final, extremely precise process. In the next part, we'll explore electrolytic refining, the stage where copper is purified atom by atom, and where industrial chemistry meets electrical engineering at its most elegant. After smelting and basic refining, copper finally looks like a finished metal. It is solid, shiny, and heavy. But for modern technology, this is still not enough. Electrical systems demand extreme purity because even tiny amounts of unwanted elements can increase resistance, cause overheating, and reduce efficiency. To reach this level, copper must undergo electrolytic refining. The process begins by casting the impure copper into large, flat plates called anodes. These anodes are suspended in massive tanks filled with a carefully controlled liquid solution containing copper sulfate and sulfuric acid. Between the anodes, thin sheets of almost pure copper are placed. These sheets act as cathodes. When an electric current is applied, something very precise happens. Copper atoms leave the impure anode, dissolve into the solution, and then travel through the liquid toward the cathode. There they settle and attach themselves in an orderly way, forming a growing layer of extremely pure copper. Impurities behave differently. Some fall to the bottom of the tank as sludge, while others remain dissolved in the solution. This separation is not mechanical. It happens at the atomic level. Over time, the cathodes become thicker and heavier as pure copper builds up layer by layer. The process is slow and carefully monitored. Temperature, electrical current, and chemical composition must be tightly controlled. Any deviation can affect the final quality. When the process is complete, the cathodes are removed. What remains is copper with a purity of almost 100%, suitable for the most demanding applications. These copper sheets are then melted again or mechanically processed into wires, pipes, sheets, and components for electronics, power grids, and industrial machinery. At this point, the journey from stone to high-performance metal is essentially complete. But copper has another remarkable property that makes it even more valuable in the modern world. Unlike many materials, copper does not lose its quality when recycled. In the next part, we'll look at how copper recycling works, why it saves enormous amounts of energy, and why recycled copper is just as important as newly mined metal. One of copper's greatest strengths is not just how well it conducts electricity, but the fact that it can be reused again and again without losing its properties. From a technical point of view, recycled copper is identical to newly produced copper. That makes it one of the most important materials for a world that is trying to save energy, resources, and time. The recycling process starts with collection. Old power cables, motors, transformers, plumbing pipes, electronic components, and industrial scrap are gathered from buildings, factories, and infrastructure that has reached the end of its life. This material is sorted carefully because copper is often mixed with plastics, insulation, steel, or other metals. These unwanted materials must be removed before melting. Once cleaned and separated, the copper scrap is melted in industrial furnaces. Compared to primary production from ore, this step requires far less energy. There is no need for mining, crushing, flotation, or complex chemical separation. The metal is already there. It simply needs to be purified and reshaped. During melting, the copper can be refined to remove any remaining impurities. The result is molten copper that can be cast into bars, rods, or plates, ready to be turned into new products. From an electrical point of view, this copper is just as good as copper made from freshly mined ore. The energy savings are enormous. Recycling copper uses only a fraction of the energy required for mining and refining new metal. This also means fewer emissions, less waste, and less pressure on natural resources. As the world moves toward electrification, renewable energy, and electric transport, the demand for copper continues to grow. Recycling helps meet that demand without endlessly expanding mining operations. There is also a strategic side to recycling. Countries that can efficiently recover copper from old infrastructure are less dependent on imports and long supply chains. Copper becomes a material that circulates through society, moving from one generation of technology to the next. An old building's wiring can become part of a wind turbine. A discarded motor can be reborn inside an electric vehicle. The same copper atoms may serve human technology for centuries, constantly changing form but never losing their function. In the final part, we'll step back and look at the entire journey as a whole, from raw rock deep underground to the copper that powers modern civilization, and why this metal will remain essential in the future. When you look at the full journey of copper, it becomes clear why this metal is so fundamental to the modern world. It begins as ordinary rock hidden deep underground. That rock is blasted, crushed, ground into powder, chemically separated, melted, refined, and purified atom by atom. What emerges at the end of this long process is a material with properties that are almost perfectly suited for the age of electricity. Copper conducts electrical current extremely well. It is flexible, durable, and reliable. These characteristics make it irreplaceable in power grids, electronics, electric motors, renewable energy systems, and transportation. Every time electricity flows through a cable, copper is quietly doing its job in the background. As technology advances, the importance of copper continues to grow. Electric vehicles require far more copper than traditional cars. Renewable energy systems depend on massive networks of cables, generators, and transformers. Data centers, automation, smart cities, and modern industry all rely on fast and efficient energy transfer. None of this works without copper. At the same time, copper stands out because it is not a one-time resource. Unlike many materials that degrade when reused, copper retains its quality through endless recycling cycles. This allows society to build a circular system where the same metal can move from one application to another over decades or even centuries. Recycling reduces energy consumption, limits environmental impact, and strengthens long-term resource security. In this sense, copper is not just a metal. It is a foundation material for civilization itself. From the first electrical systems to the technologies that will define the future, copper connects energy, industry, and innovation. So the next time you see a simple copper wire, remember that it represents an extraordinary chain of science, engineering, and human effort. From deep underground to the heart of modern technology, copper is one of the quiet forces that keeps the world running.